Hello guys, welcome to my channel. In this video, let's see properties of cyclic code. So for a n comma k cyclic code, there exists a generator polynomial of degree n minus k given by g of x is equals to g0 plus g1x plus g2x square plus so on gn minus k x power n minus k. So basically the degree highest degree is n minus k from until there will be there for a generator polynomial. So basically this generator polynomial is like a generator matrix in the linear block code. How we wrote a generator matrix, same here it is a generator polynomial. So this polynomial can be written from n comma k like g0 plus g1 into x plus g2 into x square plus so on gn minus k till x power n minus k. Okay, this is a generator polynomial. Now this is the first property. In the second property, the generator polynomial, basically one of the thing is the generator polynomial is unique in that it is the only code vector of minimum degree n minus k. Now coming to the generator polynomial g of x of a n comma k cyclic code is a factor of x power n plus 1. So what is saying is there is a we know n value, right? For example, 7 comma 3, let's take 7 comma 4. Let's take 7 comma 4 where for a generator polynomial of a n comma 7 comma 4 cyclic code, there is a polynomial that is x power n plus 1. Here n is 7, so x plus 7 plus 1 will be divided, it will be divisible by generator polynomial g of x. Okay, so what he is saying is when we divide x power n plus 1 by g of x, we will get a coefficient, but perfectly it will divide, we will get only coefficient, no remainder will be there. So h of x, that h of x is called parity check polynomial. Okay, parity check polynomial, that's what h of x is called. So basically what will tell, multiplying generator polynomial with parity check polynomial will be resulting a x power n plus 1. We will get x power n plus 1. So if you know g of x, it is enough to find h of x, because anyways x power n plus 1 is already we know it, and we know, so it's x if 7 x power 7 plus 1 like that. So from that we can find h of x. Now if g of x is a polynomial of a given n minus k and it is a factor, so what is in the third point, it is the reciprocal of it. Here we are taking n minus k is a cyclic code we are telling, and now we are writing as this, right? What we are writing, when you is a g of x is a factor, when n minus k is a cyclic polynomial. Now in this third point, what we are telling, if x power n plus 1 is a factor, g of x is a factor of x power n plus 1, then that n comma k will be a cyclic. In the reverse way is saying. Here first we are taking n comma k as cyclic, and then we wrote this expression. Now we wrote this expression, and then we are telling that it is n minus k is a cyclic code. So vice versa and like that. If the code vector polynomial v of x can be found by using v of x is equal to dx into gx. The same in the linear block code where we wrote c of x, c is equals to matrix c is equals to data into generator polynomial, matrix d into generator polynomial. In the same way here also generator matrix there. Okay, here in the cyclic code we use polynomials, right? So we instead of c we wrote v, that's it. The code vector, that is v of x, is equals to, or we can in simple terms that v of x is equals to d of x into g of x. Okay, d of x is the data that is written in polynomial way. So 1 minute. So basically we'll get v of x is equals to dx into g of x. Okay, so to write a generator polynomial, as I said, we will write this, but we will get a non-systematic cyclic code. When you write directly d of x into g of x, we will get a non-systematic cyclic code we will get. Okay, so basically how it will be, let's see. So like basically if you want a systematic, okay, if you want to generate a systematic code, then the procedure is we need to first multiply x power n minus k, this value, this term, not text. Okay, x power n, we need to multiply x power n minus k with d of x, and then we'll get some resulting polynomial that should be divided by g of x. When you divide, there will be a remainder, right, r of x. That remainder polynomial should be taken, and that polynomial should be converted into bits. Basically, the coefficients of r of x should be added in front of coefficient of d of x. Okay, then we will get systematic. Basically, the difference between systematic and non-systematic will be, in systematic code, cyclic code, we can identify the code word. We can identify the date message in the code word itself. Like here you can see all in systematic, what is happening, we are placing the redundant bits in front of the data. Basically, see here, this is a d of x, we are placing in front of this redundant directly, so they will be separately placed. Okay, okay, they are, all the data bits will be in one place and all the redundant bits will be in place. In the non-systematic, all will be intermixed, so that's why it's not systematic. That's it. So if I want to, in an example, they are saying they have given a generator polynomial 1 plus x plus x cube, and they have given a 7, 4. We know what we have to do. So v of x is equals to d of x into g of x. So they have given a data as 1 0 0 1. When you try to write it in a polynomial form, first is 1, right? So x power 0 quotient is 1, so 1 plus x quotient is 0, 0 into x plus 0 into x square plus 1 into x cube. You understand, right? So x power 0, x power 1, x power 2, x power 3. These are the quotients. So what is the resultant polynomial here? After this 0, this term will not be there, so remaining are 1 plus x cube only will be left. So g of x is already given. We will do arithmetic modulo to arithmetic multiplication. Normal multiplication is the, you understand, right? If there is a repeating term, we will take. So if it is repeating twice, you have to delete that. So x cube repeating. So these two x cubes will become 0. So same way we'll write this. We wrote an expression like this. Now this is the code vector, but not, it is not a code sorry. So code polynomial, as when you want to write in terms of bits, we need to write all the coefficients. Okay, so first is x power 0 quotient is 1 plus x 1 into x plus, there is no x square, that means 0 into x square, and x cube also 0 into x cube plus 1 into x power 4, 0 into x power 5, x power 6 into 1. So basically how to find the maximum, the highest degree of what should be there is, or how many bits should be there is n bits, right? That is the code length. Code word length is n, right? So you should say there are 7 bits or not. If for example here the x power 6 bit is 1, okay, fine. For example, if I got only 1 plus x power 4, what you have to do? We need to take that up to x power 6 it should be there, no, because the total number is n is 7. We are starting from 1, 2, 3, 4, 5, 6, 7. Sorry, from 0, x0, right? So 0 from x0, x1, x power 0, x power 1, x power 2, x power 3, x power 4, x power 5, x power 6, total 7. You understand it? So like that. For example, if it is x power, if it is a 6, 3, then up to from x0 to x power 5 it will be there. Like that you need to write. So from that we will write the code vector. This is the code vector. Like that for another data we wrote a code vector. Like that for every other also we are writing, for every, taking all the what you call, all the patterns of that bits, that is 7, 4. So basically the message is a 4-bit number, so 4-bit patterns we all wrote. 2 power 4 16 combination will write. For everyone you have to multiply that with g of x, and then we'll get this. So this is a code vector, this is a table for a code vector for all the possible data bits. But how do you say whether it is cyclic or not? We need to rotate and check, right? So let us take this one. So when you take first one, when you rotate, it will be the itself only, so no problem. When let us take this one, 0 0 0 1, that code vector for that is 0 0 0 1, 101. Here don't confuse that here this first 4 and first 4 are matching, here also this one and this one is match. No, because we can already see it's not like that. You see, if you 0011, here it is not 0010, so we can't say that. So this is not systematic, that's why we can't, they won't be like a sorry, this is not systematic, so that we can't identify what are the data bits inside the code vector. All will be mixed. So first, now let's see whether it is cyclic or not. So how to find? Here 0001101 we got. Here I will shift it by 1 bit towards right. So when you cyclically rotate, you should cyclically rotate. That means this one will become will come at the here, and it will be moved that side. So basically 1 3 zeros. So here we can see for this 1 3 zeros, like here is there. Now if I try to rotate this one more time, that means 0 will come 0 1 3 zeros, 0 1 3 zeros, here it is there. Now if I rotate again, this 1 0 1 3 zeros here. So basically those rotations will not be in the like in the same order, randomly they will be, but they will be present in any one of the position. Okay, it not like only like if you rotate it will be in the next, it will rotate, it will be like, it's not like that. Somewhere it will be definitely present in the table. So symmetric. So let's try the symmetric. So this is don't see that, only this is the formula for a reminder. R of x we will do, right, x power n minus k into d of x by g of x. Here we will do d is equals to, they have given as 1001. So for that the polynomial is 1 plus x cube, and we multiplied this with x power n minus k, that is x power 7 minus 4, that is x cube. We multiplied 1 plus x cube with x cube, we got a some polynomial. We need to divide this with g of x, we will get a remainder, that is x square plus 1 as x square plus x. I already told how to do division in the previous videos. Okay, so this is the remainder, x square plus x. What we will do, we will take this as so for this, what is the 0 1 1, right, because for lower to higher we need to write. Here there is no term as 1. 0 into x power 0 term is 0, so 0 plus x, that is x, this term is there 1, and x square is 1. Okay, here also number of redundant bits is n minus k, right? So our polynomial should also have the highest degree as n minus k. Okay, that means here sorry, highest power, not highest power, the total number of quotient should be n minus k. So here 3 we wrote, that's why we wrote 3 quotients. The code vectors, we just add those at the beginning of the, we just attach this redundant remainder bits at the beginning of this data, 0 1 1 1 0 0 1. So like that, if you make a table, it will be looking like this. So you can identify here. So 0 0 0 1 0 0 0 0 0 1 0 0 0 1 0 0 1 1 0 0 1 1, like that. Here also, if you try to rotate, it might not be in the same if you try to rotate this, it might be placed, it will be somewhere. So 1 1 0 1 1 1 0 1, so see here it is there. So it might be, it will be present somewhere in the table, but it is not in an order like that. Okay, so this is how we need to find code vectors using cyclic codes. Now how to find generator and parity check matrix. So basically for generator matrix, what we will do, basically they will give oh sorry, wait, this is matrix. Actually they will give only polynomial, right? Generator polynomial they will give. So from that generator polynomial we need to find generator matrix. So how to find? Initially they will give 1 plus x cube they have given. So from this, what we can write in terms of bits, right? That is 1 1 0 1. Yes, so basically 1 1 0 1 for 1 plus x cube. Okay, this is for general. Now, but basically how many bits should be there? there should be n bits. How many? So there are 3 0. We append 3 zeros to make it n bits. Okay. So now it is n bits. Now what to do? We just need to rotate them. Okay. So the size of this generator matrix will be basically k cross k cross n. Okay, the size will be k cross n. Here wait, so k cross n it will be there in this. So first we need to rotate again, and again we need to rotate. K means here what is that? 4 into 7, right? That means 4 rows should be there. Already one row is there. Now for the second row we need to rotate it once. So 0 it will come 1 1 1 0 1 0 0. Just I am moving this here. You understand, right? And this will be come to the front. Okay. Same way here also. Again third row. This 0 will come into the beginning. 0, and this will be moved here. And again this will be coming at the front. 0 0 here, and 0 1 1. The 4 rows you got. Okay, now we will stop. We will stop rotating because the maximum number is 4 only, no? So we got the 4, and we have to stop the rotation. So that is the matrix. Okay, generator matrix. Now coming to but when you look at the generator matrix, it is not in the form of pi. Okay, as we know, either we can take IP or PI depending on how the matrix look like. For example, in this case, if you observe this, so in this, if you observe in this, if you observe, this matrix set is similar to identity matrix, but only if you modify few rows, like if you apply few row operations, it will be converted to identity matrix. So that's why I am using G as a PIK. Okay, basically for G there are two ways. Either we can write either we can write PI or IP. Okay, but here I am taking this because when you look at the matrix, the second half is more similar to identity matrix. That's why if I take first k bits, no, it will be difficult. Okay, from that observation I am taking like that. So what we have to do, it is not okay, basically this is not not all the elements are like, see, it is IK, right? The dimension should be IK, identity matrix, that is 1 0 0 1 4 0. Okay, 0 1 0 0. Here 0 0 0 0 1 0, but this is 1 here. So when we will get this term as 0, I will XOR this third row with first row. Okay, that means third row is equals to third row XORing with first row, where row operation, this is a row operation. Okay, when you do like that, this row will become like this. Okay, 1 1 0 0 1 0, bitwise row operation, you understand, no? One like that. So this is also converted. Now for this, the third column, what we have to do, we need to XOR both with, see here, first we will XOR this line with first row. What we'll get, we'll get 0 some values, right? From see this with some values, like when you do it 1 0, it will be 1 1 1 0, and it is 1 1. So 1 1 is 0, again 1. You understand? Wait, I'll write this here only. So here only what happens, this will be 1 1, this is 0, and this will be 0 1 0 1. Again I will XOR it this second row. Then what happens, this bits will be changed to 1 0 1 0 0 0 1. Okay, you got no the same way, because we need to change 2 bits, so that's why if you like that, you need to check with how many rows. If I or like do row operation, this will be changed to our requirement. If sometimes if I do XOR operation with only one row also, it might convert, so we need to choose a best row. Now coming to what happened, this code was converted. Now this you can identify the identity matrix, this one. So the remaining matrix is called the parity matrix, right? This matrix is the parity matrix. So now I use this generator matrix to find the code vector. That is, I will multiply the data with this generator polynomial, so generator matrix. We'll get the code vector. So systematic. So anyways, we are done in the neat order, right, in this PI format. So that's why when we try to multiply D into G, we'll directly get systematic code only, because this G is actually we modified that G. We modified in a neat in a PI format. That's why when I multiply this G, we'll get a systematic code only. But in the previous cases, when I directly multiply D with G, it won't get a systematic, because the G is not refined as PI. Okay, here we refined it as PI. That's why we got a systematic directly. Now parity check matrix H, how to find? First, we know that a property that x power n plus 1 is equals to g of x into h of x, right? So in this we'll divide, so when we divide this x power n plus 1 by g of x, we'll get h of x. That means parity check polynomial will get, that is the coefficient. So this coefficient again we'll write in what you have to do, take that coefficient, that is h of x, and inverse it. That is substitute x in place of x, substitute x power minus 1. So how it will become 1 plus 1 by x plus 1 by x square plus 1 by x power 4 we will get. So now we need to do LCM. So if you do LCM, we'll get the numerator as 1 plus x square plus x cube plus x power 4 divided by x power 4. That x power 4 you take it to this side. So this is what you get. So basically this is a code. Is for this polynomial, what is the code? 1, the x term is missing, so 0, x square is there 1, x cube is there 1, x power 4 is there 1, and remaining 2 are not there. X power 4, because this should also be n bits, right, code. So this should also be n bits. We are only got 4 bits, that's why we put 2 zeros extra. That means 0 into x power 5 plus 0 into x power 6. So now this is the first row. So next what you need to do, same way, in the same way as the generator matrix, what is the first row? 1 0 0 1 0 1 1 1 0 0 1 0 1 1, right? 1 0 1 0 1 1. Now same way, cyclically rotate 1 1 0 0 1 0 1, again cyclically rotate 1 1 1 0 0 1 0. This is the, because this dimension is n minus k cross 7n. Okay, the dimension of H matrix. So that's why after 3, n minus k is 3, so I will write only 3 rows. After that I will stop. Now coming to, again we need to refine this in what format, because as we have taken G as a PI we need to take here as IP. That means not IP, what you call in minus k to P transpose. Okay, so first we need to identify what is in minus, like we need to get what is in minus k. In minus k is 3, so that's why I need 3 cross 3 identity matrix you need to form. Here 1 0, here when you transfer this to 0, it is fixed, because 1 0 0 0 1 0 0 0 1, right? So what we'll do, we'll just if I will XOR this with this last row, we'll get as 1 0 0 1 0 1 1 0 1 0 1 1 0 1, sorry 1 0, like that. So this is the new refined H matrix. Here we can see this is identity matrix, and this one is the transpose, P transpose. This is how we will find generator matrix and what you call generator matrix and parity check matrix. So we'll see how to implement how to implement this same thing. This is mathematically we have implemented, right? In practically how to implement, we will see in the next video. Thank you for watching. Like, share and subscribe.